Hello, everybody. So today we're on part 3 of the colon cancer project. I shared the link in the details, but you can follow along with this link in the chat. I'm on day 2 of antibiotics, and it kills all the bacteria, and it's letting a cold sore develop on my right side of my lip because I feel all that tingling sensation. So I have to be careful with that. And I am drinking beer. Oh well. I have to replenish my probiotics too. My probiotics. So I have something left over, so I'm going to take that. And we're actually supposed to be taking that all the time, but that's so expensive. I don't want to take it all the time. I've been eating healthy, so I need to cut back on the sugar, but oh well. And then I was able to follow along with a YouTube video, and it actually was helpful, and I knew it would be because I seen it after I failed the last time I tried to install it, and that big thing wouldn't come off. So this time it came off enough, not the way that it was in the video, and I didn't have to take off the sway bar, and I did have to move stuff around. I had to take off like the whole caliper, the brake housing, keep the brake pads in line because they have this weird thing of like being in there with these sharp metal things, and then take the rotor off, and then I had to loosen up the spring top tensioners or whatever, and then I had to take off the bolts enough, and then I had to bang that big housing arm and get it to fall off the little nut so it could move. And then actually, before I could even take off the rotor, I couldn't even get my screw in there, and I realized I don't even have a cool wrench, and then the drill is too large to fit in there, so I need to restock with some larger 15 millimeter to 22 millimeter wrenches. And then I also need to get a 1/2-inch adapter for my 1/4-inch wrench, and then the large 1/2-inch wrenches. The 90-degree one's fine, but there's one that is an obtuse angle. It's like, I don't know, it's like 110 degrees. I don't know. It's weird. So that one, I don't like that one. But I was able to use like some grippy pliers and then a wrench. I had to like find everything, so it took longer. So it did take me like about an hour and a half to finally put it in, and it did go in once I was able to loosen everything, and it slid right in. So now my 4x4 is great. But the only thing that does suck is that I have a cold sore developing right here. So hopefully I can like de-stress, and then like this will get stuff going. I've been getting my sunlight, vitamin D. I've been eating my protein, my carbs and stuff. I need to cut back on the added sugar. I've been getting enough sleep, so we'll see. And then I have a root canal coming up. So I was questioning the pharmacist because I like my dentist. Don't get me wrong, but I don't really want to be using too much antibiotics, but if I need it, for sure, because I don't want endocarditis, because she did say I have an infection in my tooth, and she had to clean it out. But then the root canal is going to clean up the infection too. But then it's also going to be digging into my, my jaw, and I have bone graft in there too. So whatever that bacteria is, I guess because it is a cold sore, herpes virus 1. That's why I don't like going to the dentist, because I feel like they are not sanitized enough, and like they're passing around shit, but also it's a lot of stress on my gum line. They're really good at what they do though. But when you work in and out with all those different oral cavities, and they're like blood and infections, and then they're wearing gloves, but like they're going room to room because they're rushed. It's just, who sits down and is that clean? Unless you have someone who wants to see you clean, because she does not want to get a herpes virus or impetigo or, HPV, any herpes family, warts, I don't know, what's a thrush, fucking colds, chickenpox, measles, whatever. So yeah, Epstein-Barr virus. Hello. Yeah, I don't want that. fungal infections. That stuff's disgusting. I mean, they're dealing with people's mouths like all day. So I don't know. I can drink a little bit of beer. I am taking this 3 times a day, amoxicillin. I'm not allergic, but apparently it is stressing out my immune system because I didn't have a cold sore right after it, but right after I took this for a day, I woke up in the morning and I felt that tingling sensation right there. And that is where you have to like open your mouth really wide, and it's like all dried out right now, but because she's like in there like trying to take my tooth out and stuff. And then she was like cleaning it out, and then she had to get in there and like put in some bone graft stuff. Okay, I'm going to share my screen, and then we're going to go over this. Okay, this is what we're looking at. Let me share my screen first. That would be helpful. Entire screen. Okay, I don't take advantage of it. I always talk to myself. And they appear to not care about what I have to really say because they always put it the other way anyway. So, I mean, technology has downgraded. I cannot even type a sentence without it incorrectly typing like every other word something else. And then when I try to say it, it doesn't hear me either. So I'm like, what's going on? They should be improving, not making things worse. All right. So yeah, we went through the series, we found out what it is. They took out the ARCA gene. We made it as far as getting the fold changes to the baseline colon cancer cell. Oh God, I'm like wiping away this fluid as it comes up. And then we had the fold changes. We got the top genes. We filtered out for those larger than 0 and removed the infinities. And then we had some genes. We looked it up on KEGG, KEGG. And then we found for colon cancer, when we searched it, we found the top genes. We listed those genes out. And we are going to see, I think we saw, did we see if any of our genes were in this list? Because this is the screenshot we got from KEGG. A lot of genes. Okay, so we'll see. So this is the list. And then we do have some genes. Yeah, we did look to see which ones were in that list of colon cancer genes. And we actually, in all the data, actually. So in all the data, we have it, but it's not necessarily in our top genes. We should now look to see if it's in our top genes for colon cancer before we look up what each one is. So let's just go into our document. We're going to go ahead and open our colon cancer. I feel like I got this on the desktop already, though. Oh, it is. It's right here. Okay, I don't know why it went that far away. Okay, so we're going to just open up this last R markdown. We'll just run all the chunks. So we're just going to run all of it. It's already in this directory, but we can go ahead and set the directory. I don't know how to be overly friendly, so I realize that if that's what you're used to. Wow, are you really gonna have a hard life? Okay. Oh, good luck finding all those people to satisfy that expectation. Nobody is that friendly. All right, so let's go ahead and just say this is part 3. We'll just leave some that and some asterisks, some equal signs. Part 3. Okay, so what did we name that one? Okay, so here's our list of KEGG genes. Okay, these are the ones that are in the list. Let's see what their fold change value is. I really don't like that it adds in the plus and the minus. So let's just go ahead and that's the fold change, fragments per from fragments per kilomillion, fold change. This is the transcripts per million fold change, and this is the counts fold change. So this is over the knocking out of ARCA over the baseline. So let's go ahead, and it looks like all of them are the same. We went over that, so they should be, because I mean, it's okay. So as in, like, they're greater than 1 or they're less than 1 across the rows. Yeah. So okay, so let's go ahead and order the. Oh, wait, these are ordered. This is the KEGG data frame, and we got one that's ordered. Okay. Let's just make sure that we're leaving off where we left off. Okay, down-regulate. We already got the down-regulated genes. So this is where we left off last time. And we have the up-regulated genes. So KEGG up and KEGG down. Let's go ahead and look at those. Let's get rid of these data tables in our viewer. We'll go ahead and save it. And then we'll just look at the KEGG down and the KEGG up. Here's the KEGG up. All right, so these are all overexpressed, upregulated. So we got EREG, DLC1, AREG, PTG, FRL, TG, FBRT. I feel like that was a gene that it was the other study was looking at. MLH1, CT, and B. You get it all the way down the line. These are upregulated in the fold change. So they knocked out ARCA, and then these were upregulated. Now these other genes, they knocked out ARCA, and these ones were downregulated. And they said that knocking out ARCA is going to make the colorectal cancer patients more tolerable to treatment, meaning they'll have better success with their chemo instead of resistance to it. So it will slow down the colon cancer. These ones are downregulated. BUB1, SMAD2, MCC, all the way down. All right. So, of course, ARCA is because they inhibited it. So it should be, right? All right. So we were going to look up each one. But let's go ahead and see if these genes all together, the KEGG ordered, can predict colon cancer or actually, let's just see if it can predict wild type or ARCA knockdown. Okay, so we'll just have two classes: wild type colon cancer and then ARCA knockdown. First, test out our genes in the up and down regulated or stimulated and inhibited genes together to see if they can predict the class as the untreated wild, I don't know if that wild type WT colon cancer, or if they predict the colon cancer with ARCA inhibited. Yes, not completely knocked out. Okay, so we need to make a matrix. We're going to go ahead and just look at this again. We're going to go ahead and just use the KEGG DF ordered. All right, so for the samples, though, we're going to have to use either fragments, transcripts, or counts. So, okay, yeah. So let's just use the counts. Okay. So let's look at the column names of KEG, DF ordered. And then we're just going to take the account one. So that's going to be 14, 15, 16, 17, 18, 19. And the gene symbol. So we'll just make a data frame out of that. It's a data frame for the matrix. I'm just naming it that. And we'll do DF, KEG DF ordered. And we're going to use all the rows, but for the columns, we want the first one. And then we want the 14th through the 19th column for the counts. Now, the class, we're going to make it right now. It's going to be wild type. And then it's going to be ARCA inhibited. So we'll just copy and paste that. It's only 6 samples. That's really terrible, but it is what it is. So we'll see how good it gets. And then for this one, and then we'll go ahead and make the matrix. So it's going to be KEG 41 MX. And it's going to be data.frame transpose KEGG DF MX. And it's only going to be 14 through 19 of the columns. We're going to leave out the gene symbol 1. It's going to be the header. Column names KEG. It's going to be column name. Oh, it's going to be KEG DF MX by gene symbol. And then we'll add the class column as dot factor class. Now let's go ahead, just because we ran all the code, we have the R marked down already. We're going to look at the table. It should be a matrix. Let's see. Oh, okay. So, oh yeah, that's right, because it doesn't have that many columns. So I need to change that because I wasn't thinking. Yeah. So that's right there. But this one, it's going to be 2 through 3, 4, 5, 6, 7. Okay, there we go. Right. Okay. Yeah. Because okay. Yes. 2 through 7. Okay. See, that's why we check. So we only have 6 samples. We have a lot more genes than we do samples. But we're going to go ahead and see what happens when we run a random forest with just 6 samples. I think we've done this before. So we'll just do the same setup. Random forest is the best classifier. All right. So we'll just pick two from we'll just manually pick two from each class, and that'll be our training set, and then one from the other one, and that'll be our testing set. Okay. So training. Oh, let's set the seed too, because that's gonna work for the random number generator. Training is KEG 41MX, and it's going to be samples 1, 2, and 5. And then all the genes. Testing will be the other numbers. I'm just manually doing this. So 3, 4, and 6. Oh, you know what? We should have that one. Okay, so 3 and 6. This one will be 1, 2, 4, 5. Okay. Now let's run that. Okay. Let's just do table training by class. Yes, that's what we wanted. Table testing by class. 2 samples in each group. Testing by class. Okay, I must not have did this right. Yeah, I didn't. Okay. I forgot the comma to separate the columns. And 1 in each one. Great. So now we're going to go ahead and run our random forest library. So let's go ahead and load that. You should have it installed already with install.packages, and then parentheses, quotation, random, and then forest with a capital F, all one word. Let's put warning equals false. It sucks. Okay. Now we're going to go ahead and make our random forest model. We'll just do random forest, KEG 41, random forest, and then we're going to do the training set. This is just training the model, and it's going to be, okay, 1 through 41. And then the Y target outcome variable is training by class. Yeah. And then M tries, because we have 41 genes, we're going to divide it by 3. So that's like about 13. We'll just put 13. In trees, we'll just do 5,000. Confusion equals true. Importance equals true. Now let's do RF KEGG 41, the name of our random forest model, by confusion to see the confusion matrix. Okay, great. So it predicted, it looks like these 41 genes are great predictors for these 2 classes of colon cancer wild type or colon cancer with the ARCA gene inhibited, as there is 0 class error and 100% accuracy in classifying each sample correctly. For the 2 ARCA inhibited class samples, they were all correctly identified as such. And for the wild type, they were also all predicted correctly. Let's let's look at the importance. Okay, hopefully this doesn't ruin our prediction in predicting, because sometimes that happens with this. I don't know why, but I was doing on another project, and I couldn't do the predict after I ran importance. So I want to see what it's gonna label all of these genes as. So we're gonna do RFKEGG41 by importance, and let's just see what it says. Okay, so this is the importance. This is how much weight it had. The genie. So every time it's has an error when it runs it, because it does a sampling, it groups them together in 13, and then there's one out bag. That's usually the default method, and it from those 13 it says, oh, it's most likely this, and it keeps doing that. But then if it gets it wrong, there's an error, the genie error, which it puts a weight on certain values. You can look it up if you want to. It's a robust classifying system. So yeah, so I just wanted to put it up there. But now let's go ahead and predict. It looks like there's some negative weight for C, C, and D on how it predicts for the orca and the wild type. As you can see, some negative weights. So every time that one was in the sample, there were some negative weights in how it classified. But this classifier did great. Let's see how the model predicts on the holdout set. Okay, so let's go ahead and predict KEGG41. Predict. We're using the RF model, this one, on our testing set. And then we're going to make the matrix to show results equal data dot frame predicted equals predict KEGG41, and actual equals testing by class. Let's go ahead and print the results. Oh, great. It actually did. So, so the results were as expected with 100% accuracy in predicting the wild type or the orca inhibited sample. Okay. Well, okay. So now we are going to say these genes are a good set of genes for predicting whether the sample is wild type or orca inhibited. These are not necessarily our top genes, though. So let's see which of our top genes made the K top 41 genes for colon cancer. Let's save this. So we're going to these genes, top counts genes. Let's just look at the column names. We'll probably just merge them. All right, column names of top counts genes. It looks the same. Top FPK. Yeah, and then column names, top TPM genes. Let's add a column to identify where it is. Oh, actually, I'll do that. We're just gonna merge all of these and then see which ones are in all of it. So we're gonna have to add some more chunks. Okay, and then we're just going to combine them. We're not really going to merge them. We're just going to row bind them. Okay, so due to top 3 sets. So our bind top counts genes, top FPKM genes, top TPM genes. Page table data top 3 sets. All right, so we have 60 genes. Let's see if any of these are in the list of genes in the KEG 41. Okay, so top and KEG. Let's make it all caps. Okay, so we're going to use top data, top 3 sets, which the top 3 sets by gene symbol in percent KEG DF ordered by gene symbol. And then let's print it out. It's possible. Nothing now. There are none of our top genes in. None of our top genes are in the KEG data. So let's see if any of these genes can predict the class of the sample as wild type or ARCA inhibited. Let's do so by the data of 20 top genes per group. All right, so we're going to go ahead and do the same thing and see if these genes in our top genes can predict these 2 classes. All right, so we will go ahead and go over to top counts genes. Let's do that one. So our column names, let's just do it in the console. Top counts genes, our gene symbol. Okay, so we're doing the counts again. So we're going to go ahead and take 1 and 14 through 19 as before. So top counts DF MX. We're going to go ahead and do top counts genes, columns 1 and 14 through 19. And then we're going to go ahead and let's make the matrix top counts MX data.frame top. Oh, This I didn't spell it right. Top. Oh, it is lowercase. Never mind. Oh. Top counts genes, but only 2 to 7. Column names top counts MX are top counts, no, top counts MX by, we don't, top counts DFMX by gene symbol. I think that's what it is. Right. Yes, it is. No, it's not. Gene symbol. And then counts MX by class as dot factor class. Names. Top counts genes. So all the genes are there. Column names top counts MX. 20 observations by 6 variables. Top counts. Okay, hold on. So it's doing it right here. So we went ahead and took the columns that we needed, just the counts in the gene symbol, and all the genes, the 20 genes, are on the rows. That was our data frame to make a matrix. And then we have the top counts again for the matrix. It's a data frame, and it's we're transposing only the counts because the gene symbol is going to be top. Oh, it's going to be top counts genes by gene symbol. And then top counts MX by class. Top count. Oh, yes, this one needs to be lowercase. Ugh. Top counts genes. Top counts genes by. By genes. Okay, so it needs to be the length of the vector. Okay, so we have top counts. Because we didn't transpose it by. Okay, you gotta transpose it. Okay, now let's just look at it just to make sure. We should just run it again. All right, yeah, so there's the samples. There's our 20 genes at the top. For the count, going to be top count MX. And it's rows 1, 2, 4, 5. All the genes and the class. Testing is top counts C3, 6. Let's see how each class. We're going to go ahead and set our seed right here too. There's 2 in each, so that's good. Now let's see how many are in our testing set. Okay, great. Now we're going to go ahead. Let's save this. And we're going to make this the RF model for counts 20. All right, random forest. We're going to use a training set, and it's 1 through 20. And the target variable is training by class, which is the 21st variable. Because if you look at our training set, 21 variables like it should. And try with 20 genes, a third of that is about 7, but we'll just say 6. Entries equal 5,000. Confusion equals true. Importance equals true. Let's look at the confusion matrix. Let's see if these genes are any good. Oh, look at that. The same perfect results with 100% accuracy in predicting the class in a 2-class model. Let's see how well it predicts the holdout validation testing set. So we'll go ahead and look at predicted 20, predict RF counts 20 on the testing set. Results, let's make our data frame. Predicted equals predicted counts 20, actual equals testing class results. Let's print it out. Okay, great. So also 100% accuracy in determining the class of this 2-class model. We just need to do the prediction evaluation for the other 2 types of media as FPKM and TPM. Okay, so all right, so now we're going to do the same thing. This one, I'm going to get a little bit of water. And then we're going to go ahead and work on the FPKM, or fragments per kilo million of the gene, these top 20 genes. Ugh. Wow. Okay, so let's go ahead and do that. That's the top FPKM genes. We already know which ones because all the variables are the same. So let's just go ahead and do top FPKM DF to matrix equals data dot frame. No, we don't need to make the data frame. It is actually top FPKM genes, and it's going to be the 1st and the 14th through 19th columns. And then we're going to go ahead and do top FPKM matrix equals data dot frame transpose top FPKM DFMX. Only the second through seventh, seventh columns, and then column names top FPKM MX are the top FPKM DFMX by gene symbol. And let's add the class feature. Top FPKM MX by class equals as dot factor top FPKM no, it's not. It's class as a factor class. It has to be a factor whenever you do classification for the random forest model. Let's go ahead and look at what this looks like. Great. So we have our 6 samples. We have our 20 genes and our class with the 6 samples, 3 of each. Let's save that. Now we're going to go ahead and do our training set, which is going to be the same vector, which is going to be top FPKM MX. And it's going to be rows 1, 2, 4, 5. And the testing set is going to be top FPKM MX. And it's going to be the 3rd and 6th rows. Let's go ahead and set proceed for randomness to be the same each time we run it. Let's look at how many samples are in each. Two of each, that's as expected. Let's look at the testing set. 1 of each, that's what we wanted. Okay, now we're going to make our random forest model, and it's going to be the FPKM 20 random forest, and then we're going to do training 1 through 20. Target is training by class, which is the 21st variable. M-try is about 1/3 of 20, which is about 6 to 7. So we'll go 6. Entries equal 5,000. Confusion equals true. Importance. We didn't run the importance on the last one, but it was like perfect. So I mean, we'll go back and do that. And then let's go ahead and look at the confusion matrix. I guess this one. So this one's also for our training model on the top for FPKM, colon cancer, and predicting the wild type colon cancer, or the colon cancer with the AURKA gene knocked out. All right, so now for prediction accuracy, we do this. Predicted FPKM 20. Predict RF FPKM 20 on the testing set. Results, build our data frame. Predicted equals predicted FPKM 20. Actual equals testing by class. Let's see our results. Okay, great. Perfect again. Again, let's look at the importance of these features. So you go to RF, FPKM20 by importance. And actually, we can go up here and just add that chunk too. Because we did name it its own model, so we can look at the importance. RF counts 20 by importance. We don't have to do anything. That's what it was, because we saved the model right there. If you're running out on memory, you can start erasing variables, but usually computers today that aren't just made for the cloud have enough memory to hold all that. All right, so we're going to go ahead and do the last one. Is a TPM. Now for the top 20 genes of the TPM, or transcripts per million genes. So we're going to go ahead and make our top TPM DF to MX. It's going to be the same columns. So top TPM genes, columns 1 and 14 through 19. And then top TPM MX, we're just going to transpose this into a data frame, data.frame, T parentheses, top TPM genes, but only 2 through 7. You can for that, but we already know it because of the other ones. And then we're going to do column names, TPM MX. We're going to name them top TPM genes by gene symbol. And then we got to add our factor of class top TPM MX by class as dot factor class. It's the same for all of these. And let's look at the outputs. All right, good. So we got the 20 genes on the top with the class feature. Let's go ahead and get our random forest model built. All right. A random forest RFTPM 20 random forest. Oh, you know what? We got to make our training and testing set first. Okay. So let's do that. Set.seed. That's going to be 1, 2, 3. Training is going to be top TPM MX. And it's going to be the rows 4, 5, all the columns of gene. Testing top TPM MX, rows 3 and 6. All the path. Let's see how many are in each. Good. In each, great. And then let's see how many are in the testing set. One in each. Great. Now we're going to do a random forest training on the first 20 features, and our target variable is the 21st one, which is training by class. There are 20 genes we want to predict, so our Y is going to be 6 like the others, because it's 1/3 of it. Entry equals 5,000. Confusion equals true. Importance equals true. And then we're going to look at the confusion matrix. Ugh. Spelled it wrong. No big deal. Oh, look at that. Same perfection with 100% accuracy in predicting the correct class. Let's see how well, how the importance is for these features. Gene features are RL, TPM 20 by importance. All right, yeah, we just have it right there. So whatever UTP14C is, it got negative weighted. It was special. Everything else had a certain positive weight. All in the thousands. Nothing in the hundreds. Okay, so now let's see how well this model predicts the holdout validation set. Predicted TPM 20. Predict what is it? RF TPM 20 testing. Let's look at the results, build our data frame. Predicted equals predicted TPM 20 equals testing by class. Let's look at it and see. Oh, look, 100%. This is great. All genes for each group predicted 100. Seeing these two classes of wild type colon cancer or AURK inhibited or knocked out group or class. Okay. From here, we will now look at what our genes are that had much change in the AURKA knockouts compared to the wild type AURKA non-inhibited colon cancer cells. So we will be going to GeneCards. We will go to genecards.org to look at this side by side. And I'm actually going to do that at another time. I know we were going to do that today, but I guess that's going to be all for today. Go ahead and catch this one. It's been, almost an hour. I feel like, It's are really great for looking at that kind of stuff. So we'll be doing that Saturday night. All right. All right. Have a great night.